Hello and welcome. In this video I'll be covering section 4.3, which is over polynomial division, the remainder theorem, and factor theorem. My goal for you by the end of the video is to be able to perform long division with polynomials and determine whether one polynomial is a factor of another, to be able to use what's called synthetic division to divide a polynomial by a binomial of x minus c, to be able to use the remainder theorem to find a function's value such as f of c, and to be able to use the factor theorem to determine whether x minus c is a factor of some function f of x. So with regard to how division in this scenario is going to work, remember when we divide, we always obtain a quotient and a potential remainder. So that's still going to hold true when we have a polynomial being divided by another polynomial. We still are going to get what we would call the quotient, and then at the very end, if there's anything extra, then I would say that would be the remainder. If the remainder happens to be 0, then we actually could say that that must truly be a factor of whatever you're dividing, or the dividend. So what we do for this, we have kind of two strategies. One of them is called long division. The other one is called synthetic division. So the first example I'll work through is just how to do this utilizing long division. And I'll show you also how to write or identify what the actual quotient is and what the remainder is. So to set this up, what we'll do is we'll take whatever I'm dividing and put it inside of a long division symbol. So in this case, that would be the x cubed minus 2x squared plus 5x and then minus 4. Always be mindful if there's any terms missing from whatever the highest power is and then down. So power of 3 on this first one, a power of 2 on the second one, a power of 1 on the third one, and my constant did not skip any terms, so I didn't need to have any sort of placeholders like a 0. The thing I'm dividing by, well, for part A it says I want to divide it by x plus 1, so x plus 1 then is the part that goes out front. How long division really works is I want to take whatever is in front on the outside and think in terms of what could I multiply this by. So in this case it would be the x. What could I multiply that by such that it would match the first term that's on the inside? So in this scenario it would be x cubed. So if I multiplied x by x squared, that would give me x cubed, so that would be the number or the term that I would write in the numerator. At this point, I actually distribute through both parts of what's in front. So it'd be x squared times the x in front, which is x cubed, and I just line it up with its corresponding like term. Then I do the same thing with the second part, x squared times 1. That would be a positive x squared. And if we think back to how long division worked with just numbers, I would now subtract vertically. So since there's more than one number or more than one term, I'll group it, put a negative in front. So technically you could just distribute the negative right off the bat, but ultimately I'll just remind myself I'm subtracting each time. So x cubed take away x cubed is going to cancel out like I was intending. A negative 2x squared minus an x squared, that actually would turn into a negative 3x squared. The last two terms, since there's nothing to subtract from them, essentially just look like they just drop down. Then I move on to the beginning term now being negative 3x squared and think, how can I make the x that's in front by multiplication match that perfectly? Well, if I multiplied by negative 3, that would be a good start, and I have 1x. I need it to be x squared though, so more than likely multiply by an x as well. And do the same thing we just did with the x squared, distribute it through the two terms I have in front. A negative 3x times x is the negative 3x squared. And then a negative 3x times a positive 1 would actually be a negative 3x. But once again, I'm going to subtract, and it looks like both of those came back negative, so when I subtract a negative, this actually will switch to addition. So the first term being a negative 3x squared minus another negative 3x squared, that really would cancel out like I was wanting. And then I have 5x take away a negative 3x. Well, that take away a negative would switch to addition, so this really is 5x plus 3x, so that would give me 8x in front. And then the minus 4 didn't have anything to subtract from it, so it's just going to drop down once again. And I just continue repeating the process. Now I want to match 8x, so I would need to multiply the x that's all the way out front by a positive 8, so I'll put plus 8 at the top. If I do multiply by 8, the two terms I would get would be 8x, and 8 times 1 would be a positive 8. And just like I've done in the previous two lines, I subtract that result. And so 8x minus 8x would cancel out, in fact. A negative 4 take away 8 actually would turn into a negative 12. So our quotient, the result that we got here, would have been the x squared minus 3x plus 8. The remainder is what I end up having down here. So this would be what I call my remainder. So how I deal with that when it comes to rewriting, like what would this actually be? Well, I would essentially write what I have on top, x squared minus 3x plus 8, and then I just put whatever my remainder is. So since that was negative 12, I could say that that's the same as minus 12 over what I was dividing by, which was the x plus 1 in this case, so it would just be over an x plus 1. And so that would be the result, or an equivalent statement of what happens when I divide that long polynomial, that cubic, by the linear polynomial x plus 1. And in this case, since that was not a remainder of 0, I wouldn't be able to say that x plus 1 is a factor for this specific polynomial. Move on to part B. The setup is essentially still the same. I've got x cubed minus 2x squared plus 5x minus 4 inside, whereas now I have x minus 3 on the outside. And my goal still remains the same. Make the term out in front match whatever the front term inside is by multiplication. So I would need to multiply by x squared to make that x cubed. Go ahead and multiply it. So I've got x cubed minus 3x squared. Group that up. I'll subtract vertically here. So x squared minus x cubed minus x cubed would cancel. Negative 2x squared minus a negative 3x squared. That would switch that to addition. So I've really got negative 2 plus 3, which would be a positive x squared. And then the 5x and minus 4 just tag along because, again, there was nothing to subtract from them, from my product. Then I'll move on to the next part, make it match x squared. Well, that would just be multiplied by a positive x. And let's go ahead and multiply it. So that would give me x times x is x squared, and x times the negative 3 would give me a negative 3x. Group it, I'll subtract. And so x squared minus x squared does cancel like I wanted. A 5x take away a negative would switch to addition, so 5 plus 3 would give me 8x, and then minus 4. Still just drops down because nothing was there to subtract from it. So my last thing here is going to be make the x match 8x. That would just be multiplied by a positive 8. So I've got an 8 times x in front and an 8 times a negative 3, which would be a negative 24. Once again, group it, subtract, and the first term would cancel, 8x minus 8x like I wanted. A negative 4 minus a negative 24 would switch to really plus 24, so negative 4 plus 24 is positive 20. So my final result for this one would be the x squared plus x plus 8, the quotient that we got, plus the remainder, since it was positive this time, over what I'm dividing by, which is x minus 3. And once again, because this wasn't a 0 at the end, I would be able to now confirm that x minus 3 is not a factor of that particular polynomial. So as far as just what was being done right there, again, that was just a review of how long division works, just now applying it to polynomials. Notice if you think back to how it worked with numbers, the process is very similar in the fact that I'm looking for what can I multiply the number in front by to stay below whatever number is inside, or whatever number I can create with the first 1 or 2 or 3 numbers, depending on how big the numbers are you're dividing. And then we just subtract and come up with what the next line is and almost reset to come up with the next value. In this scenario, though, it's more of a combining like terms situation we're trying to deal with, and we're actually trying to eliminate terms completely until I finally get to the end where the degree would be less than whatever I'm dividing by. But anyway, when we divide a polynomial by something, in this case we'd call it a divisor, the resulting polynomial q, or capital Q, is something we can represent for the quotient, and the polynomial capital R of x would be able to be something we could call the remainder. So the quotient does have to drop in degree, so in other words, the degree has to decrease from whatever the original problem was. After all, if I'm dividing, say, like a power of 4 by something that had a power of 2, that really should drop the power by 2, because I can't have x squared times something higher than x squared and still remain an x to the 4th. So again, every time I divide, the powers do decrease, so just kind of keep that in mind every time you do it. In fact, it should, if you're dividing by a linear, or like an x plus 1 or x minus 3 like the last example, it should really just drop by 1, as you could see with the last two examples. I started with a power of 3, and the result, the highest power I had, was then a power of 2. When it comes to how can I check to see if this was correct, or is there a different way that I could represent it, I personally like it to where I represent it the way before, but we also could write it as whatever I was dividing by would be like the coefficient. So whatever the divisor was, notice, would be in front. I could say that that would multiply with whatever the result was above. So that would have been the two quadratics that I got on the last two examples. And then at the end I could just say plus my remainder without needing to write it as a fraction. So again, there's two different ways to represent it. I kind of like the way, or I prefer, just because that's how it's always been presented, or moving into a higher level class. Usually we go with the format I presented, not so much this one. But it is technically a different option that we could go with. So again, we could relate them in this way, or we could even say that p over x, well, I guess it would be divided by dx, would be equivalent to the quotient of x plus the remainder, if it still had an x, over what I was dividing by. So this format that I just wrote really was what we were going with the previous part. If I actually didn't want to have the left side be divided, notice I could rewrite it the other way, which would just be multiplying everything by d over x, so, or d of x, sorry. I'm assuming most of you probably are, I don't know, feeling a little bit intimidated by the long division, just because there's a very high likelihood of making a mistake with the subtraction portion. Plus it's just kind of a confusing concept in general, and it takes up a lot of space. So the next concept I'll cover is what's called synthetic division, which does work for a specific type of thing that you're dividing by, but it's technically not a fully universal, hence why we still need to show how the long division does work. Alright, so that concept that I just mentioned, synthetic division, is a way that I can actually do this whole process without having to worry about writing all of the x's every step of along the way. So if I'm asked to divide some polynomial, as you can see here, the f of x, I've just utilized a bunch of different random variables. This would have been a quartic polynomial, if you want to think of it that way, because the highest power I included here was 4. But hopefully you can kind of see that it would just continue on in this fashion. No matter how many different terms I have, I just write all of the coefficients, which again, the coefficients are just the numbers in front of the variables, including the constant at the end. That still is considered a coefficient. I would write all of the coefficients in this area, and I kind of set it up to where I draw this little box up here in the top left, and then I just draw a line at the bottom. I usually do the box first, write the coefficients, and then make sure that I leave space enough. Notice there's kind of this open space right here where I'll be able to add some numbers or introduce some numbers here, and when I work through an example or two, hopefully this will kind of come together. But again, I only write the coefficients, so it would be in this case a, b, c, d, and e. And then whatever the 0 is of the thing I'm dividing by, which in this case it does have to be a binomial of degree 1. So it does have to be a degree 1 binomial. Now if I said for this one, or for this example, if I said what is the 0 of x minus k, well the 0 of x minus k, if I were to set that equal to 0, I'd add k over to the other side. So the 0 actually would be positive k. So what we do is we actually take that 0 of the divisor, whatever I am dividing by, in other words, and I just put that number up in this box. Now how the process will eventually kind of go is the vertical idea is I'm going to add, and since there's no number right now to do the diagonal pattern with, you can always picture like there's always going to be a 0 here, which really just makes it look like the first term will always just drop down. So I don't ever really write that 0, I just immediately drop that number down, and then it turns into, I look at the whatever number goes below the line, I multiply by the number in the box. So in this case that would just turn into a times k, and then vertically I add. So everything vertically in this case is actually addition, so there's a little less likelihood of having a negative error or a mistake with negative signs. So if I were to add this, I would have b plus a times k, or I could write that as a times k plus b. And then I would do the same thing. I would multiply that result by the number that was up here, so it would be a times k, so a times k squared plus b times k, and it would turn into a new number. Now, with this being all variables, it's probably very confusing, but once we actually have numbers in here, you'll notice that this is relatively fast, and at least in doing mental math, where I can just multiply by a number and then add it, and then multiply, and then add it. So again, everything vertical, every time I'm going this direction, I'm going to add, and then any number, the newest number I have that's resulted underneath the line that I drew right here, I end up just multiplying by whatever is up in this box. And then that creates the number that would go in the next spot, and then I add again, and then repeat, come up with a new number by multiplying, and then add vertically, and then multiply again, come up with a new number here, and then add. Whatever this last number is, oftentimes I just kind of out of habit, I just draw a barrier right here to represent whatever is in this bottom right area. That's what we would call the remainder. Whatever is in this area over here could be a list of multiple numbers. In this case, it more than likely would be a list of 1, 2, 3, 4 different numbers. So at that point, those become coefficients of whatever the quotient is, so I could then throw x's back on, just realizing if I took a power of 4 for this example and divided by technically something that has a power of 1 right there, my new power for this one would now start with 1 less than the power that I started with, so it would start with an x to the third, and then the next term would have an x to the second, and an x, and then my constant. So each term just kind of counts down by 1 with the power. So really, if you can just figure out what that first power is supposed to be, each term after it just drops by 1. Now, if a term ever happens to be missing, so let's say I had this starting with x to the fourth, but then it just somehow skipped over this x squared maybe. Let's say that term just completely got skipped over. I'd have to put a 0 in that place where that corresponding variable should have been, or that corresponding coefficient should have been. If I forget to put those zeros there, then it really does mess up the whole process, and I get usually everything from there on as an incorrect response for those terms, and then that would then make my remainder in the end actually be off. But anyway, just kind of pointing out some of the possible pitfalls of this, or possible curveballs that get thrown at you. But again, synthetic division is specific to binomials that have a degree of 1, so if I ever had a power on this x, like in this area right here, if I ever had a power right there, I'm forced to kind of go through and do long division. But if I notice that there isn't a power on that x, I should be able to follow through with this kind of shortcut that simplifies and doesn't take up near as much space. So let's go ahead and get an example here out in the open. So I'm going to go ahead and just set up the box here. So the box is going to have whatever the 0 of the thing I'm dividing is. So if I have x plus 3 that I'm dividing by, the 0 of that would be -3. So that's going to be the number that goes inside this box. Then I set it up with my coefficients. Well, it looks like I've got a 2, a 7, and I actually skip over the x term, so there needs to be a 0 in this spot, and then a -5 for the last part. So I'd have for the x cubed a 2, for x squared a 7, for x, well, that's missing, so a 0. And then my constant's always the last one, so a -5. Then I leave enough space for numbers to go underneath there by just drawing a line about that far down. And now I just basically start my process. So again, the first number always looks like it just drops down because there was no number to add with it. Then I multiply going back up to this direction, so 2 times -3 would give me -6. And then vertically, once again, I'm adding, so 7 plus a -6, that would give me a +1. And then I repeat, 1 times -3, so notice I'm kind of doing a circular pattern in a way. 1 times -3 comes up with the next number, so -3 would go here. 0 plus -3 is -3. And then -3 times -3 would give me +9, and -5 plus +9 would give me 4. And again, usually I just draw a line for that last one to represent, okay, whatever is in this bottom right corner, that's the remainder. Everything in front of that line is going to be coefficients on my quotient. So since I was a power of 3, I divided by something that was a power of 1, I'm hoping it seems reasonable that this now is going to start with, instead of x to the third, it's actually going to start with x to the second. And again, the 2, the 1, and the -3 that I found are just going to be coefficients on each term. So since the next one is a +1, I know it's going to be a plus sign, and the one after x squared would be x, so that's going to be an x term. And then I'm to a constant. I've run out of powers to put on x, so the last one's just going to be a -3. And I could, like I did earlier, write the remainder over what technically I was dividing by, which, look back at the original, I could put it over the x plus 3, and there we go. So as far as what is the quotient, well, the quotient was this part. That's the quotient. And the remainder was what I identified right here. And we can put it into an equivalent format, or here's what actually it turned into when I divided it, by just saying it's always the remainder over whatever you were dividing by. I'm sure that example was probably relatively confusing because it's a brand new concept to you, but I'm hoping you can also see how much more simplified that process really became, because I didn't have to worry about having x's multiplying with other x's or trying to match powers or anything like that. It was really just line up numbers and add vertically and then multiply to come up with the next number. So it simplifies that process, and notice it also didn't take up near as much room as some of the earlier examples when we did long division. Now the next type of example I'm going to work through, we're still going to use synthetic division, but now notice the binomial has a little bit of a different situation to deal with, in the fact that there's now a coefficient in front of the x. It still has a degree of 1, and I still can find the 0. So again, the 0 of this guy would be, if I set that equal to 0, I would add 1, so it would be a +1, but then I would divide by 2, so I actually have my 0 is 1/2. So that'll be the number that goes up in the box. My coefficients, if I look at what I have, I start with a power of 3, so I usually just kind of count down. I should have a power of 2 next. I have that term. It's got a -1 in front of it. I should go to an x to a power of 1. I have that term. That'll be a -32. And then after that, it should just be my constant, which I don't need to put the plus sign. I don't know why I did that. It's just a +16. Then I'll draw the line, making sure, again, I leave some space for some numbers to exist. And I'll drop this first one down because there's no number there, so 2 plus 0 would just be 2. Again, I'm adding vertically. To come up with the next number, I would multiply, so I'd have 2 times 1/2. Well, 2 times 1/2 is 1. -1 plus 1 is 0. Then I go, okay, well, I've got 0 plus 1, or 0 times 1/2. That would just remain 0. -32 plus 0 would remain -32. And then a -32 times 1/2, well, that would turn into a -16, and a 16 plus a -16 actually gives me 0. So again, drawing that line on the end, my remainder in this case actually was 0. So the conclusion I'll get to make, which we'll talk about a little bit more here in just a little bit, is that that actually is a factor for this particular polynomial. Now, the issue now I have to kind of think about is, well, this time it was a fraction, whereas last time it wasn't. How do I now adjust? Because if I divided something like 2x cubed by something that starts with 2x, I'm hoping it would seem reasonable that the 2 probably shouldn't be a 2 anymore, because 2 divided by 2 actually should turn into 1. So what I now do with these numbers here, these new coefficients, is because of the 2 that was in the denominator, I'm actually going to right here just say, well, I need to divide everything that I just got in front of this line I drew by 2. So that would make this 2 turn into a 1, 0 would remain 0, and negative 32 actually would turn into a negative 16. So again, I'm just dividing each of those 3 numbers by whatever the denominator of the fraction was. Now I can actually throw the x's back on. So again, I was a power of 3, I divided by a power of 1. So this first term, hopefully it's reasonable. If I have a coefficient of 1, I don't need to write it. But its power now is going to be 2, or it's going to drop from the original 3 down by 1 to come up with a power of 2. Since the middle term has a coefficient of 0, technically the x term would be canceled, and then the last term would just be a minus 16. And if I wanted to, I could say that this really has my remainder over what I was dividing by. But what's 0 divided by anything? Well, it's 0, so really I can drop that portion of it and just realize that if I were to divide these two things, I actually get this polynomial, x squared minus 16, that now if I wanted to factor that even further, I have a strategy to deal with. That actually could turn into an x plus 4 and an x minus 4 if I really wanted to. And that's kind of where we're headed. We're eventually going to get to a point where we want to be able to take these things and dwindle them down to where I actually have all of the factors. We just still haven't quite gotten to the point where we figure out how do I come up with what thing to try to divide by initially such that I could get it to turn into maybe a quadratic and fall back to some of the quadratic strategies we've been exploring. So now on to the next main topic we want to talk about today, which is what's called the remainder theorem. So essentially, if I have some number c that gets plugged into a function, result would then be f of c. So keep in mind again, f of c would mean I plug c in for all of the x's, and whatever result I got would be the y value. What the remainder theorem says is if I actually create my own binomial of x minus whatever number I'm plugging in, so notice again the c is what goes into the function. So if I wanted to actually figure out that in a slightly different way, especially if there were a whole bunch of terms, I could actually just say, well, let's pretend like I'm dividing the original function by x minus c, whatever the remainder is, so in other words the r, actually is equivalent to the y value of the function when I plug in c. So the synthetic division idea is actually a way that we could maybe a little bit more efficiently evaluate a function at a specific value. Now when it's a large number, getting plugged into something that has a very large power, oftentimes the numbers start growing and you'd have to use a calculator anyway, so it kind of defeats the purpose of using synthetic division, but we're going to go ahead and practice a few, at least in here as well as in your practice, that hopefully will make it kind of make sense how we can still arrive at that final answer, but in a completely different way than maybe we normally would do via calculator. Especially if it's a small number, usually it's going to be easy to do some mental math with small numbers. It's just once that number starts getting too big for us to be able to do mental math, then this idea of utilizing the remainder theorem kind of loses its moxie in a way. But the next couple of examples are going to just kind of show how we could do this and what that truly would equate out to. So here we go. As far as these ones are concerned, these numbers I intentionally chose to be a little bit smaller just so it can kind of go a little bit faster with the mental math. But if I said to do f of 1, that really would not be too hard to just plug 1 in everywhere x is. And really that would just turn into whatever 1 minus 26 plus 11 plus 25 would equal. And again, we could use the calculator to come up with that. But again, I'm going to kind of show a little different way to do it that simplifies the process in a way. So with this, I would pretend like I'm dividing by x minus that c value. So again, the 0 of that actually is equivalent to the number I'm doing. So instead of having to picture it that way, really we can just say whatever number's here is going to go up in the box. So like with this next example, it's going to have a -2 that goes in that area. Outside is going to be the coefficients. It looks like if I started with a power of 4 and then went to a power of 2, I must have skipped over that power of 3. So this is one of those scenarios, once again, or I need to make sure I put a 0 in that spot. So my power of 4 had a coefficient of 1, my power of 3 was missing, my power of 2 had a negative 26, my power of 1 had an 11, and then my constant at the very end was 25. Again, draw the line, and then now I'll go ahead and change color here so we can kind of see which numbers I'm now introducing or creating. The first number just drops down. 1 times 1 would be 1. 0 plus 1 is 1. 1 times 1 still is 1. Negative 26 plus 1 would be a negative 25. A negative 25 times 1 would be a negative 25. A negative 25 plus 11 would be a negative 14. A negative 14 times 1 would be a negative 14. And a 25 plus a negative 14 would give me 11. And again, drawing that line, this right here is my remainder, which actually means, because of the remainder theorem, that I can conclude off to the side here that f of 1 is actually equal to 11. All the other numbers really are not that important when it comes to just evaluating a function at a value. I just wanted to figure out what would the last number possibly be, and that actually is what we would get. Now if we go back to the original and maybe say did this the way that we would have done before, which would be just plug 1 in everywhere x was. 1 take away 26 would be negative 25. Add 25 to that, that would give me 0, and then add the 11, that gives me 11. So notice it kind of confirms that this process actually does work, at least for this specific example. Take my word for it, that it should always work so long as I'm actually doing my math correctly and adding vertically and multiplying to come up with the next number when it goes to the diagonal part. So we'll go ahead and set up the next one. Same exact numbers, since it's the same exact function that I'm plugging into. Draw my line, and let's go ahead and drop the first one and multiply. So 1 times negative 2, negative 2. 0 plus negative 2 is negative 2. Negative 2 times negative 2 is positive 4. Negative 26 plus 4 would be a negative 22. Negative 22 times a negative 2 would be a positive 44. And 44 plus 11 would be 55. And 55 times a negative 2, that would be a negative 110. And a 25 take away 110 would give me a negative 85. And again, whatever that last number is, that's my remainder. So at this point, I can now say that the function at negative 2 should be equivalent to negative 85. And notice I didn't have to do any sort of pressing powers on my calculator, which plugging a negative in with powers getting involved sometimes can cause some errors. So here it was just simple adding and multiplying over and over and over until I got to the final end result, which then it would give me what the y value of the function is when I plug negative 2. So kind of a nice, sweet trick that the remainder theorem can do with regard to just evaluating a function at a specific number. Alright, and now on to the last main topic we're going to talk about, which is what's called the factor theorem. And technically we've already kind of presented this in a way, in the fact that if I had the remainder come back equaling 0, then I can then say that x minus that number would actually be a factor. So hopefully it would seem reasonable that if I said that a 0 for this was, say, like maybe an example, this is not related to this problem in any way, shape, or form, but let's say I knew a 0 was 1. Think backwards and go, well, what parenthesis must I have set equal to 0? Well, what is 1 a 0 for? Well, it's not going to be plus 1, it would have to be a minus 1. So it'd kind of be like taking the 1 and moving it over with the x to try and force it to turn into 0. So your parenthesis always looks like it's kind of the opposite of whatever the 0 is. So notice again it has this format of x minus the number, and whatever that number is inside would be considered the 0. And why we would know that is because from the last slide, remainder theorem says if I wanted to evaluate the function at c, I would just do synthetic division. The result should be the remainder. Well, this is saying that the remainder must have been 0, and that's again why our conclusion can be, well, that means it went in perfectly, so I actually could call that a factor, and whatever the result is, maybe I could factor that even further, which is really what this last example is going to be. Notice it says to completely factor this polynomial, but it's going to give me what one of the factors is at this point. and the very end, then it wants me to actually solve for what all of the zeros of the polynomial would be. So notice for this particular polynomial, if I said go ahead and try factoring with what you currently know, I'm assuming we would try grouping, and we would recognize when I take things out, I'd have an x minus 3 from the first parenthesis, but then I would have, let's see, I can take a 2 out of those two. I'd have a negative, or actually a positive 3x and then minus 4. Those definitely are not the same parentheses, so factoring by grouping would fail relatively fast. So this is kind of telling us here that I want you to know that x minus, or x plus 2 is one of the factors, which then means one of the zeros has to be negative 2. And so that'll be the number I'll actually try. So negative 2 is going to go in that box. My coefficients, I've got a power of 3. A power of 2 has negative 3 in front of it. A power of 1 has negative 6 in front of it. And then my constant, so this one didn't skip any terms, so I didn't have to introduce any zeros. And I just do my synthetic division process. So first number drops down, multiplies by the number in the box, negative 2. Add it vertically, I get negative 5. Multiply, I get positive 10. Add vertically, I get positive 4. And 4 times negative 2 is negative 8. And I get a remainder of 0, which was what we expected to hopefully happen because I told you it was going to be a factor initially. At this point, though, we throw the x's back on. I was a power of 3 originally. I divided by something that had a power of 1, so my new power, again, these right here are the coefficients. So I'm going to go ahead and rewrite it as 1 times x squared, so x squared, minus 5 times x. Each term, the power on the x just decreases by 1. And then the last one must be a constant. Well, notice that created a quadratic. I should be able to factor that. In this case, the factors I would use would be what multiplies to 4 that will add to negative 5. Well, that should be a negative 4 and a negative 1. So the factor version of that quadratic would just be x minus 4 times x minus 1. And in the first part of this said completely factor it. I get to take the one that they gave me and just tag that one on at the end. So notice I really just kind of dropped that one down right here, but I needed to divide by it in order to be able to get to the quadratic to come up with the other two factors. So as of this point, I've done the completely factor portion right here. Notice a power of 3 turned into 3 separate parentheses, all with powers of 1 or multiplicities of 1 if you want to think of it that way from an earlier lesson. So again, that power can kind of help you identify how many different sets of parentheses you should have when it's all said and done. In this case, notice 3 matched the 3 parentheses. Now when it comes to the actual zeros of this function, since it did say solve the equation for when is the function equal to 0, I guess this is, since it's a solve, not tell me the zeros, it's really just going to be what does x equal. Well, it should just be whatever makes each parenthesis equal 0. So the first one would have been positive 4. The second one I would add 1, so positive 1. And the last one I would subtract 2, which really, again, that was the first number I did up here in the box. Whatever's in the box would always match whatever the 0 is for that particular, I guess, factor, if it truly turns into a 0 at the very end. So hopefully this is kind of coming together here at the end. We've done, it looks like, what, about 4 or 5 or 6 different examples of how synthetic division works. My hope is by the end of the video it's starting to make sense how to set it up and how it actually gets executed to be able to turn into a new polynomial that has a smaller degree. Ultimately, the goal when you do synthetic division, especially if you're trying to do this factor idea, is eventually do it as many times as possible until you get it to this quadratic idea like we got down here in the bottom left. Because once it's a quadratic, we have strategies to try, such as the ACB tables, or we could even try completing the square if I was setting it equal to 0, or last resort would be, let's just plug it into the quadratic formula. Hence why we've had you guys practicing doing those steps at the end of each of the practices thus far. Anywho, hopefully this video has been helpful, but if you do have questions, just reach out to one of your teachers, either myself or Ms. Bass, and at that point we'll do whatever we can to make it make sense for you. I appreciate you taking the time watching the video, and we'll catch you next time.